Hello, my name is Joe and this is Sierra Specialty Auto. Welcome back to the shop. Today I'm going to work on a water pump, or going to begin work. I think this is going to be a two-part series. Begin rebuilding a water pump for a Crosley engine in a 5 kilowatt Army surplus generator. I'm sure it's World War II vintage, equipped with a cast iron Crosley engine, not the copper brazed Cobra, so-called Cobra engine that was sometimes used. I'm sure the military would not have been interested in that particular version of the Crosley engine. So let's get over to the roll-around cart, take a look at this pump and what's wrong with it, take a look at what other people, specialists, shall I say, were unable to fix, and see how I'm going to fix it. Here's the pump body with the impeller, and I'm kind of concerned about the condition of the shaft. It does not look too bad, and it didn't feel too bad coming out of that bushing. That's very minimal wear either. And a bunch of little hardware. Here are screws for the pump, fit the pump body, and some rope packing. And here's a spring, no doubt, to apply pressure to the seals of brass. These are the end washers for the chevron seals. I hope they fit these, and they appear to. A male end and a female end, and that does appear to assemble nicely. And an extra, and I don't know, perhaps this was used as a shim to set the tension on the pack. I'm not sure about that. And we have, I'm hoping, a set of 6. There's 1, 2, 3. I think that's 1, 2, 3, 6. There's all 6 screws. So now the question is, can I remember well enough how to put this back together? The impeller is bronze. It looks to be in excellent condition. There is a plastic, I'm going to guess nylon, but that could be UHMW, it could be some other plastic, and it appears to be the original, and it appears to be in very good condition. And that's what's going to make this seal, right? Or, well, no, it's going to be reinforced by all of these. Okay, so that's, again, that's a very tolerable fit. You got to have a little bit of room in there for some lube. I don't think there's more than 2,000 or 3,000 clearance there. It spins freely. Now I want to see how far down those seals start working. They run from about from about 2 7/16 up to about 1 1/2 from the end of the shaft. Excuse me, 1 1/4 from the end of the shaft. Okay, and 2 7/16. Okay, so I can see the wear, or I can see the marks on there between here and here, where the seals were riding, and there is some very slight wear there. I don't think it's anywhere near significant. So when the time comes, I'm just going to polish that up and go for it. Okay, I can feel the wear as I run this down, but of course, this is a radio pattern of wear, and I'm going to feel it as I push past, but I don't think it's significant. And in here we have a mating bore, and I would expect that there would not be wear in here, but there will be corrosion. That just falls right in. So we're looking at, I would say, we're looking at having to put a sleeve in there because that seal just drops. And then installing it on the shaft is not going to add any tension to the OD. Not like a rubber lip seal where you might gain some. Okay, so that's going to be probably where a lot of that leakage came from in the first place. So I'm going to have to put a sleeve in there, and we'll use, I think we'll use bronze for this. I have a good stock of brass tube, but I think I'm going to feel better if I use bronze. So this is probably nominal sizing. See what we got here, roughly speaking. We got, well, that's nominal 1/2 inch. It's a couple thousandths under. And this is going to be, I'm going to say nominal 7/8. I get about 778 at the mouth of the bore. Let's get a real measurement on that using the tri-mic. Yeah, 777, and I did note as I was going in with this seal on the 1/2 inch shaft, a little bit of tension right at the mouth. I can feel it. I can feel it holding some tension, and then at the bottom, it's free. I wonder how many of these go in here. We have to have, I also wonder what holds this in. Where was that? Here's what holds it in. This cap. This cap holds it in. Gets upset into this groove. That makes sense. So now the question becomes, how much of this stuff can I pack in here? And I don't, well, I don't really get any clues from the wear marks on the shaft as to how many of the chevrons were in there. Do I gain any on here? That was probably down tight. Yeah, I'm pretty sure that was crimped with this all the way down, and they had to relieve the cap a little bit at this fitting. Okay, so I have, for the depth, I have 1 in 170. This is going to go in there. How tight will that go? Also I have to use at least, still don't understand why there's two of these female washers. There should be one, and those are both flat on the back and female recess. So I need maybe a couple. I need, well, I would think at least two in there. And that combination is 0.370. And what did I say I had? I had 1 and 170. .170. So if I subtract that, I end up with 800. And this spring, in the relaxed state, is already an inch. So what kind of compression do I want on that? Probably a fair amount. See if I can get an idea of what I can squeeze it down to. So let's say 3/4. 3/4, pretty good tension. How much room do these take up? I wish there were more parts in there. I wish I'd kept all the stuff that came out. 420, 450. That's within 30 thousandths. I'll bet I can get this another 30. I think that's about it. I think that's the combination I need. Three of the chevron seals plus the forward and rear spacer, the male and female, I should say, backing plate. And the spring and the cap. And that ought to work. What do I measure this at, just for curiosity? That measures a little less than 3/7/8. So when I do the sleeve, I need to do that sleeve a little tighter than 7/8. Probably need a snug fit on that. That's 60. Well, that may be too tight. 860. Somewhere between 860 and, coming up on that very gently, 870. Well, let's try something else. This amount of interference feels pretty good to me, and I think that's this is a nominal fit on a 1/2 inch shaft, and it feels good. So let's see what the difference is. Here's the tri mic up to 500, I think. At 492, it's holding itself on. 492 it holds, 491 it doesn't. So let's call that 10 thousandths. We want 10 thousandths interference on the outside as well. So that is going to be, these are plastic, of course, molded. So they're each going to be a tiny bit different. But it takes about 870 to hold them in there. So that measures 862 at all of 862. That one's about 860. So I think we're looking for a pretty tight fit on here. And where's my other one? Here it is. I'm going to have to go for 863, I think, to be safe. All right, so we need to put a sleeve in here to 863. Let me get some material for that and do a little cleanup here, get a little better organized. While I was off camera, I took some 220 paper on a surface plate and worked these sealing surfaces against it until I got it looking pretty good. There's some kind of a divot from the original casting here, but it's contained within the inner and outer perimeter. I don't think that's going to be an issue. I can hold this up to the light and get, I can find no gap in there, so that fits pretty well. Certainly the thickness of the gasket plus a very thin coat of RTV on each side will seal that up quite well. So I think those surfaces are ready to go together. Next thing I need to do, clamp this down to the milling machine, find center of that bushing, and take this out to a clean diameter of about, well, I'd like to have, I think, at least a 40 thousandths wall thickness, maybe 50. I'd like to go 100 over. I'd like to go to 975 approximately. Where does that put us? That leaves a fair amount of meat. Maybe I'll go a 1/16 of an inch. Let's go from 7/8. Let's go to 1. Yeah, let's do that. Let's shoot for a 1/16 of an inch. Take that out to about 1, and then make a bushing out of this bronze for a light press fit that we will reinforce with Loctite 640. Let's go get set up on the milling machine. Here's my setup on the milling machine. Got this just clamped flat down to the table. Don't know if you can see them. I've got some aluminum cowls in here bearing down on the rim of the pump, straight down onto the flat of the table, not onto the gap, the T-slot. Got this angle plate set here simply to hold the brace on the coax indicator. So let's turn that on, and I've already got it pretty close, probably close enough. Not going to improve on that very much. Let me take this indicating setup apart and get the little criterion boring head in there, and we'll let that out to around an inch, perhaps a little bit more. I've set the table to provide a stop. I can use the power feed to run the quill down to full extension, and when it stops, I'm at the bottom of my hole. I'm set for about a 25 thousandths depth of cut, 50 off of the diameter, and I'm at about 420 RPM, and we're at about a 1.5 inches a minute on the quill feed. Aha! I'm set for a negative 25 thousandths depth of cut. Let's try going the other way. Now let's get a rough idea where we are. And it took, there was still some uncut surface in there at 50 thousandths over. So that bore was badly corroded. And if I had tried to put this together with the new seals, the water would have just run around the new seals and poured out like a fountain, which is what it was doing before I took it apart. Okay, I'm at about 950. I'm going to take another 50. Right at 1 inch, maybe a thousandth or two under. Now here's a good reason, in my opinion, for, in a situation like this, for doing the boring first to a reasonable number, anything in the ballpark that works for the project at hand. I can't get in there with my good measuring tool. I've got the 1,000 or 1 inch to 1.2 inch intramic that I could take a very accurate reading in there with this tool. In order to do that, I have to run the table down enough to clear after marking my spot, setting a dial, whatever, for a reference point. Or in my case now, I can use my z-axis, or this would be the w-axis digital readout. But if I just take this to a number that works, whatever that number is, then I can go to the lathe and machine the bushing to fit, use the micrometer easily. I'd be able to size this after it's off the milling machine. I can get at it. So in this kind of a situation, I like to do the bore first to any kind of a number that's in the ballpark. And I think I have hit that number right now. So I'm going to take this off and we'll go over to the lathe and start making a bushing. I'm measuring my bore at 995 all the way from top to bottom, very uniform. 995 is a good number. The manufacturer of my retaining compound recommends, let's see, I shouldn't state it that way. The manufacturer measures the shear strength of their cured product at a diametral difference of 2/1000ths of an inch. So I want to make this 2/1000ths of an inch smaller than 995. I want to make it 993. So that is a fairly snug slip fit, and the retaining compound will make up the difference. At that clearance, the retaining compound itself will maintain concentricity, although there's enough give in this plastic that's not a terribly significant issue. So we're looking for a bushing. I'd already calculated somewhere. I want 10/1000ths smaller than the OD of this seal, and it falls out at about 873. So I want 863, provided this will clear. And it will. And by the way, I think I figured out why there are two female washers. One of them goes on top of the CO stack to provide a register for the spring. That seats in there nicely. So, go to the lathe. We're going to turn this down to a length of, well, we'll turn it to 993 on the OD. We'll turn it to 863 on the ID, and we'll turn sufficient that we can part off 1.150 inch length. I've set a carriage stop for my depth. Let's get a touch off and get a full cut in there, and then check with the mic and see where we are. See if we got a full cut. Yes, we did. And we are at about 835. So we have about 30 to go. Let's take 25 to start with. That should put us around 860. Actually, that's awfully close to where we want to be. I think I'm just going to take a spring pass on that and leave her be. Now we should just be able to get one of these in here. Yeah, I can get it in. I don't know if I can get it out. That's a snug fit. But that's what I was looking for. I'm going to have to get another tool to get in there and knock that out. I'm going to put another 1/1000 of an inch on that. That's just a little too tight. It's still pretty snug, and I'm going to have to reach in with this tool again because my finger is too big to get a good register in that 1/2 inch hole. There we go. But that worked much better. Now then, we're looking for 993 on the OD. And we need about 1.25 inches in Z. So I'm going to use the DRO and the depth, the carriage stop, to get a little wee bit over 1.25 inches. Now we'll take that down to 993. First pass was 100 off the diameter. Second 2 passes were 200 100,000ths depth of cut. We're at 165, 160 maybe. Let's take 60. That's it. That's perfect. Should be a very snug slip fit. And it is. Between that and the Loctite, we're in good shape. So let us put a bit of a chamfer on the bore and take the edge off with the abrasive cloth. I think I like that a lot. I will part that off to 1 and 1/50. Repeat that same chamfer technique. All right, there's our bushing, 863 or maybe 864 on the inside, 993 on the outside. See how we did for length. Looks pretty darn good. I'll buy that. And I will Loctite this in. Actually, I may use flex hone. I have a 800 grit brush hone. Put just a little bit more of a polish on the bore, and then I will glue that in with Loctite. I think this is a good place to break this video into two parts. This pump project is taking a little longer than I thought, but a good job is worth spending time on. I want to thank you for watching. I hope you'll comment. If you haven't already, I hope you'll subscribe. Again, thanks for watching, and please come back and visit the shop again.